think let us start. Okay. So today my plan is fairly basic. I'll just share my screen. You can hear me, right?
Yes, sir.
Yes, sir.
I hope you all had good festival days. Okay. It's my pen. Okay. So let's just sort of, today, so we have 3 more weeks of classes. Okay, so this is the sort of broad plan I have. So today I will just do a bit of recap and try to clear any doubts, any conceptual doubts you may have, big questions, that could be even technical points. That's one part of the plan for today. And then I want to cover one interesting calculation, very simple but very interesting calculation about stochastic processes. That's the goal for today. Okay, now let me just summarize before I sort of try to see how we will want to end this course. Okay, what all we have learned. Remember, I made this sort of diagram in the beginning. I don't remember what the axes were anymore. I think these were levels of organization, if I'm right. And this was time. So I marked this as space. I mean, I still don't know if this is the best way to represent. We said, in much of the work models we studied in the basic theoretical ecology course, we were sort of dealing with populations, right? And then we were checking how these populations change over time. So in this course, we have added sort of various dimensions to this. That was the only thing we learned last time. And there was a focus of, equilibrium dynamics and many different contexts, both ecology and evolution, right? In the context of single populations and multi-populations, multi-species populations. And then now what we have done is, we have learned, space as well as, stochasticity, not just space. In the context 4 dimensions, we also have space and stochasticity, and the new dimensions we added, right? And then we studied them at the level of individuals, right? You can think of individuals. So random walk was the classic example that we studied. How the trajectories change over time, what are the classic properties, and then we looked at how populations, if I were to just look at this, populations we studied 2 sort of, directions, population with stochasticity. So we took mean feed models of populations and added stochasticity and add halfway. And then we also looked at populations plus spatial dynamics. So we have studied all these things. So we looked at ideas like, pattern formation, during pattern formation, right? And then we have looked at how stochasticity changes population dynamics. And we have also looked at, stochasticity at a very individual level, using the random walk as an example. And this random walk was fundamental to understanding both of these concepts. Okay, now there are still some gaps in our understanding, right? But broadly speaking, if you were to think in the following way, so the biological world has individuals, right? And there is a lot of variation among individuals in the property, in their individual properties. And then there are interactions among individuals. And then these interactions are stochastic. Okay, and then all these interactions and variations play out in a spatial context. Okay. Now this is what the real biological world looks like. Right now, of course, all the things we learn in this model are basically trying to find simplistic mathematical representation. Okay. And then try to make some sense, try to make some new insights out of what to expect in these real world systems. Okay. Now, and to sort of, again, to sort of, account for all the 3 components, we had what we called, individual based, sometimes also called agent based, right? Individual based, spatially explicit. So if we had models that account for both the individual level rules and interactions, their stochasticity and variations happening on a spatial context, that's the sort of, the complex modeling scenario you can think of. And one such example that we studied was that of contact process. Right? And these models, the nice thing about them is they actually capture local interactions among organisms. And they also capture stochasticity and space. All of them are present. I'm just repeating a bit here, but these are all really important, though, especially the fact that the interactions that we capture are really local interactions. This is unlike the mean field model where we write down the roots or sort of phenomena at the population levels. So okay, now of course what you can now do is once you have defined such a model, you can just simulate them. Okay, so you can just simulate these models, which captures all the sort of details that we have input. It is still a simplistic representation compared to what the real world entails, right? So, but you can simulate, and at least within the simplified model, capturing individuals, stochasticity, and space, we can understand various properties. But then we also wanted to go a bit further. In fact, we haven't really done much of it at all, right? I don't know if I don't think I asked you to simulate contact process, right? I don't think I asked you to simulate the Vijek model or the cousin model where there are all these features are present. Okay, we haven't done those, but simulating them is one really powerful way of understanding, and because often the properties that you discover from simulations can just never be done using any analytical method. So this is really crucial, but I haven't done. I just want to emphasize, we haven't paid much attention in the sense that I haven't asked you in the homework to simulate. Okay, but it's something I strongly encourage you to do so. And these are often computationally expensive. They take a lot of time. Okay, so you need to be patient, and there is a lot of scope for making errors while coding. Okay, so you have to be cautious when you're writing codes. Okay, so that's one part, and it's something that you really need to learn. And for more and more complex models, it becomes harder and harder to write analytical models anyway. Okay, but nevertheless, we did learn some techniques for these models. Okay, and the most important one was that of mean field approximation. And the sort of the irony of this is that it actually gets rid of both space and stochasticity, but it provides some really useful baseline prediction, useful baseline predictions or expectations. Let's call them expectations. Sometimes predictions is also quite frequently used. Okay, so for example, if you started off with contact process, the density equation for the entire contact process model will look like a logistic model. Okay, and this mean field approximation also helps us link individual level rules to population level phenomena. So that's really neat. It's very useful to learn and to be able to apply this method. Okay, and once you have the equations, you have all the tools from deterministic nonlinear dynamics. I should make it clear that in fact, when I say mean field approximation without any adjectives, we often mean deterministic mean field approximation. Deterministic mean field approximation. Okay, so this technique we have learned. Okay, now the second thing we learned was that of mean field approximation with space. And of course, in the simplest cases, this space basically becomes diffusion. For a large number of cases, so here if we had an equation of the type rho dot is equal to f of rho, which is for the sort of type of equation we had. Here we had equation of this type, rho, which depends on x, y, whatever the dimensions that we have. We take the derivative with respect to time, right? And that depends on f of rho, again the same f as before, plus the diffusion. Okay, so this is what we call reaction diffusion equations. Okay, we learned how to analyze them. We needed the ideas of Fourier transforms. Of course, both the mean field approximation as well as the mean field approximation with space, or the reaction diffusion approximation, right? They can be both applied to one species systems or to multiple species. There is really no limit. And in this context, we learned that even though diffusion has this property of homogenizing things, you can still get patterns from homogenization process. That was really interesting. That's what we called, pattern formation was possible, and that came from the idea of Turing patterns, Turing instability. Okay. So this is one way to go about space. It's an analytical approximation that includes space. Of course, you still have the space in the original model. So this is one level above the mean field approximation. Okay. Now, when we had now, how do we now incorporate stochasticity? I told that you can start with the mean field approximation equations and then ad hoc noise. That is one way. Okay. For example, now this itself can arise in two forms, right? If an equation looks like this, an ad hoc noise can be what we call an additive noise, where eta t is a Gaussian white noise. It could also be a parametric noise, which often manifests as a multiplicative noise. Okay, so there are two ways the stochasticity can be incorporated. And here we have ignore the space. Of course, in a very trivial way, you can say instead of mean field approximation, I have a reaction diffusion approximation, and then likewise we can add the ad hoc noise in the exactly same way. We will have an additional diffusion term in such a case. I don't think we did that explicitly in any of the assignments or the class, but that's something you can easily think of generalizing. Okay. And then again, we learned some basic ideas about this. Okay, and then we learned that specifically we learned the following, that when you have multiplicative noise, this can lead to what we call noise-induced states. Okay. Now, in the context, okay, that's another analytical approximation that leads some interesting insights. How stochasticity can create new types of states, right? I think I gave this example of in the lab assignments, something like this, right? This plus some continuous, if I remember correctly, or the home range model, as we call it. So we did something on these lines. We showed that while deterministic equilibrium would have been zero origin, we actually find that the observed states are actually far away from this zero equilibrium. Okay, so we have a noise-induced state that is possible. Okay? That's another approach and technique that we learned. Okay. Now, this is what I think we have learned so far. I think in the last class, we learned the applications in the context of collective animal motion, about both individual based models, what are the properties. We also learned about the ideas of, concepts of emergent properties, right? And models of, binary choice, collective motion, and so on. How do we write down mean field approximations for all those cases? So we have learned, applied these ideas in various contexts. Okay. Now, so far, this is sort of a very broad overview. So any questions from any of you so far? That sort of, that's nagging you, okay, something I don't understand, something that's deeply missing from your point of view.
Yeah. So about agent-based models, I understand the simple mean field approximation, but I don't understand how we incorporate space into it, because I don't think we did that in class.
Okay. I understand your dilemma. So we did that not in a very rigorous way. We did that more as a heuristic. Okay. So for example, if we define the contact process, we know how do we get the mean field approximation, right? Okay. Now, let us say now what should be the spatial component for the contact process. That's actually not a very easy problem, to be honest. Now, but what we do know from the example of random walk is if an agent is moving randomly, okay, let's say in a two-dimensional grid, right? That can be approximated by a diffusion process. Is that something you agree?
Yeah.
Okay. Now let us assume a contact process without birth or death, where the individuals are just hopping randomly to four corners, the four nearest corners randomly. Okay, so one limit of contact process can be there is a you can try to construct this yourself. So in the contact process, if there was an individual, there was some chance of birth and death in the neighborhood, right? There was some chance of birth in the neighborhood, right? There was some chance of death of the so-called individual. Okay, so you can consider that in some limit you can think of a combination of birth and death is equal to movement. For example, there is a the movement from one cell to randomly choose a neighboring cell can be considered as birth in one of the neighboring cells with a certain death in the focal cell. Isn't that right?
Yeah.
So in that limit, contact process basically becomes diffusion. Random walk, it becomes random walk, right?
Yeah.
In that limit, basically, you're now basically now in a random walk. So basically, so now what you can now do is if the both birth and death is present, as well as now what's happening in the full contact process are actually both processes, right? There is a movement because of dispersal, which is randomly chosen neighbor, right? But there's also a birth death process. So it's a couple. So one can say that these two terms can be independently derived and they don't interact. In that limit, the reaction diffusion approximation is a reasonable approximation. Is that clear?
Yeah.
It is by definition an approximation. It's not it's a heuristic or an approximation. I haven't formally derived, and that actually does become difficult in this case.
Right. Yeah. Thanks.
Okay. Any other questions? And I think in this context, we also discussed the ideas of bistability. If I'm right, as another example, we discovered bistability, and I discussed that application. How we can use the ideas of potentials and noise to sort of think about ecosystem changes or population changes, and how we can think about constructing some indicators of population changes. Okay. So anything else? Okay. So now here, going back to the stochasticity part, right? So far what we have done is we have done I have added stochasticity in this ad hoc way anyway. Even this diffusion was done in ad hoc way, right? Okay, let's we assume that diffusion is an independent process which could be approximated as a random dispersal. Okay, and in fact, diffusion is often considered a good approximation for dispersal. Okay, so likewise, we have done an ad hoc noise here. Now, in the following, so you see here is sort of rough plan I have for the rest of the semester. Okay, so now what we will, or one topic I would like to cover is the more systematic derivation of noise that will lead to what we call demographic noise. Okay, so what is demographic noise? Basically, it captures two elements: the fact that populations are finite in numbers, they're not infinitely large, and then the rules are stochastic. Okay, so this is something we will cover. This is not an ad hoc way of doing. This would be a systematic derivation. So this is one topic I want to cover: systematic derivation. Okay. Now another topic I want to cover is the following. I think this is the only new technical topic I actually want to cover. After this, we will discuss one paper that again sort of looks at all of this in a. There is one paper I want to discuss that sort of puts all the entire thing we have learned in a very nice framework. There's a paper in 1990s that I will discuss. There's another point I want to discuss. I want to discuss an empirical example for noise-induced states. Okay, this we will discuss. These are the two things we will discuss. Maybe demographic noise is a technical point we will discuss. They will discuss. I want to discuss another technical point about Intercalculus, which I have been postponing for quite some time. This is for today. Okay, and then I will discuss an empirical example on noise-induced states, because this will help us, make connections to data. Okay, and then finally, I'll just, one paper, very famous paper by Turet or Turet and Levin. Okay, 1994. I'll discuss it. I think this will basically wrap up the entire course. Okay. So any questions before I go to today's little discussion on Intercalculus? With that, we would have discovered hopefully three empirical examples. One of, I think, Turing pattern formations, applications, right, in the context of vegetation patterns. And the second one was with the stochastic models, how we can apply in the context of ecosystem transitions, population changes, right? And third would be an example of noise-induced states. Okay, so three empirical examples we would have considered in this course, and then a whole variety of mathematical techniques which can be applied to anything. See, all the empirical examples I am giving you are biased by what I know. In fact, those are also the topics we sort of closely work in our lab. Therefore, sufficiently well to tell you, complete story. But there are many such examples. Don't think they're even, representative of the entire literature. Okay. Okay. So this is what the plan is. So do you have any other suggestions or questions that you want to see in the course before we wrap up?
Sir, so personally, I find swarm dynamics and swarm intelligence exotic. Do we have more examples of it?
What I will do is I will give this noise-induced states in the context of swarm dynamics, but it won't necessarily cover swarm intelligence though.
Okay, sir.
Any other? And further there are a bunch of talks I can recommend, and you can just watch that. There are lots of talks, very nice talks online.
Perhaps some more information about evaluating models that we come across. That might be.
Okay, value. Okay, we will discuss that. There is no one easy answer for the question, but we can discuss. Okay. Okay, cool. So I'll just go on to the sort of Intercalculus part. Okay, it's really interesting just to illustrate why technically it's actually a very difficult subject. Okay, why incorporating stochastics is so hard, and which makes also very difficult to cover them in basic courses. But they are so important for real world. Okay. So now all of us know what is integration. Let's actually hope that I could make mistakes in covering this topic, because it's very, very much possible, because I am not prepared at all. Okay, so all of us know what is integration. You learned in your high school, right? Let's think of a very simple example. Okay, I given by integral of x dx. What is this integration? It's an indefinite integral. Okay, let's put some limits. Let's say 0 to x0. What would this be? This would be x squared by 2, 0 to x0. That would be x squared by 2. That's the algebra of integration. What does it mean geometrically? You must have all learned that you basically plot x, plot the function, right? This is the function as a function of the whatever the variable, right? In this case, this is linear function. And then if it is going from 0 to x0, what you are really doing is basically the area. So it's the area below the curve. That is what I is. Any questions? I hope this is something you all remember. Now, that's the algebra, that's the geometric integration, right? We all know this really well. Now, if you now go back and look at the formal definition, it is defined as follows. If you take any integral of this type, let's say again 0 to x0 to make life easy, the way it is defined is as follows, right? What you basically do is, it's there is some function and there is some variable x, right? What you do is, let me now write a more general function. If there is some x, okay, it can of course come down. There is nothing here to ask it to go back. What you do is, you basically at x, you take a small slice, okay, at some xi, take a small slice, and then if this width is delta xi, you multiply with it. So therefore, you have this area of this sort of a trapezoid, okay. And then what you do is, you basically divide your entire range of integration 0 to x0 with many such trapezoids, and then you sort of add them up, and then you take this limit of delta xi goes to 0. So you make this trapezoids infinitesimally small, and then you basically find the areas of each of these trapezoids and then add them all up. Is that clear? At least from a basic heuristic of how integration works, right? That's how it works. And if you now apply it to any function, you should be able to find the area behind the curve, and then that, for example, if the function was just x, we will find the same answer again. It's called the Riemann integral, and this is how we do integration. Any questions on this? I hope I haven't made no mistakes. Okay, here is a very key point when I have said this. What is this xi? So let us now zoom this out. Okay, this part I have now zoomed out. Okay, let us say this is some value x. This is some value x plus delta x. Okay, this is the ith window that I have, ith trapezoid that we have made. Okay, where is this xi located? Okay, this is xi, delta xi. Where is this xi located? Is xi in this location? Is xi here? Is xi here? Where is it located? In the small infinitesimally small window. Actually, I should have a slightly different notation. I think it's a pretty bad notation. What I will do is the following. I'll maybe use capital Xi to indicate a point inside. So, what I have done is, this is xi plus 1. This is the xi. This is the ith discrete location. This is the I plus 1 at discrete location. I plus 1 location is xi plus delta xi. And the capital Xi is some value between the xi and xi plus delta xi. Okay. So xi basically belongs to xi. Is that right, everyone? Now, do you remember this definition? Of course, we assume the delta x is constant, so it's a constant is what we usually look at. Okay, here is the thing. So Riemann integral, the value of the integral that you find, is independent of a where you choose your capital Xi. Okay, that's a very key, interesting property. So it doesn't matter where you choose your the intermediate point in your integration. The basic idea is that as I'm making the trapezoid infinitely smaller and smaller, the variation of the functional value here in this window is so tiny anyway. So it shouldn't really matter whether I pick this point as the value of f, this point. So all the points are so close to each other anyway. So the exact location I choose in this window is irrelevant. Okay, that's the basic idea. Okay, let's go on. Any question? Please ask. Please feel free to ask. Okay. Now, what about stochastic? But remember, all of this was for some value of some function f of x. Okay, and something important here was f is a continuous function, right? A smooth function. It's a smooth. It's a continuous function. It's it doesn't have crazy bumps and so on and so forth. That's an important criteria for us to be able to do this. Now consider this integral. Let's call this IW. You remember this. Where so I hope all of you remember what is Wiener process. Wiener process is basically the mathematical representation of Brownian motion, right? So the basic idea is that if I take any value of the Wt, and another value Wt0, right? T prime, let us say. Okay, there are various properties that hold between them. The properties are that the average value is 0, right? And if you look at the correlations, this basically becomes minimum of T and T prime. I think we had done this in the class. Okay, and then basically this increment are independent of each other. It doesn't depend on what was the value of Wt, right? And this can be thought of as basically the jumps of random walker. Okay, this is what the linear process is. Okay. So it's created again. Okay. So now this is the linear process. Now we have defined an integration of a variable W, which is linear process, and as we know, linear process is a stochastic process. Okay. So how does that look like? If I were to plot W as a function of T, how would this look like? It would be incredibly, I can never really, of course, all these lines I'm making up pretty wrong. And if I go here and zoom in, it look like extremely jagged again. If I zoom in, it looks extremely jagged again, because at every step it's making a random decision to go to the left or right? And before there's randomness at every time step. In this case, it's a continuous time step as well. So it won't be the smooth function of the type that we discussed for deterministic or Riemann integrals. Okay. So does that have an implication? Does it really matter? So let us try to look at this. Okay. So W is a stochastic process, and what we have is an integral of stochastic process. What does that mean for I though? Okay, which means that I will also be a stochastic process, right? So I will also be it will be number, but say it's going to be not a deterministic number. It's a number that might depend on realization and so on and so forth. Okay? So therefore, IW must be thought in terms of mean variance, our standard thing set always. We always think of whenever we have the stochastic process, the basic things we must calculate are the mean and the variances. Okay. So now let's look at. So let's again now try to do integration of this IW. So remember we have this. And okay, so what is this? Now let us apply the Riemann sort of integration approach. That means we have divided time into various bins. Okay, so let's call this tau 1, tau 2, tau 3, and so on and so forth. And then what we have is dWt. What is dWt? So let's say there is some t here. Okay, so dWt means increment around this time. Okay, so now there are what this means is it's value of this at t plus delta t minus this. Okay, so this is the increment in delta t time step. This is the increment, and this is w tau I. Okay, maybe I think what I should also do is ei. So remember what we did. Okay, I think we should rewrite this. Okay? This is the time axis. I'm going to divide time axis into t1. Okay, I think it's on page. T2, T3, up to T. Okay, and then we choose some value tau within each of this. Okay, and as I told you in the case of Riemann integral, it could be typical in the deterministic integrals. This tau can be consistently the lower edges, could be high, upper edge, or could be anywhere. It doesn't really matter. Okay, so we now have to define where is our tau I, and then we will now evaluate the integration. Okay, so now what I have done is for some ti we have this is how it looks like now. Psi goes from 1 to some n number of partitions that we have made. Okay, so let us now choose some tau. Now tau can be anywhere between tau I can be anywhere between ti and ti plus 1. So let us write it in the most general way. Okay, how can we write this in the most general way? Tau I can be written as alpha ti plus 1 minus alpha ti plus 1. So what this means is that if alpha is equal to 0, that means that tau I is equal to tau I plus 1. If alpha is equal to 1, that means that it's the upper edge, upper limit. Okay. Then tau I is equal to Ti. Is that fine? So by varying alpha, I could now choose the tau anywhere in between. Is that all fine with everyone? Okay, I hope that's okay. Now, what do we have? Now we have this integral IW. Now you remember that IW should only be thought in terms of mean and the variances. Let's think of the mean of IW in the mean sense. So mean of IW will be this, right? So I have to take the average of W of Ti. I'm just going to multiply this into two terms. So by the way, Ti plus ZT is just Ti plus 1 minus okay. And then of course there is summation. Oh, nice. Is it fine with everyone? Any questions so far in the algebra? Because if you lose the algebra here, you will lose everything. Okay, no questions. I think you're all doing very well. So now we have basically summation is equal to 1 to n. There are two expectation values. Tau I Ti plus 1 minus summation again tau I omega Ti. Okay. Okay. Now let's go back. Look at the definitions of the Wiener process. The expectation of WT prime is minimum of the two. Okay. So let's come here. That means that the expectation of this is just minimum of tau I Ti plus 1 minus summation of, it again goes from 1 to n, minimum of tau I, comma, Ti. Is that fine, everyone? So we're trying to calculate the mean of this integral. Integral is integral omega, Wiener integral of the Wiener process basically. And we're trying to see what we find. Any questions so far? Okay, now let's again draw the timeline. This is time. This is I. This is tau I. So now, what is minimum of tau I at tau I plus 1? Tau I will always be the minimum of these two, right? So therefore, the first term is summation of tau I goes from 1 to n. On the other hand, if you look at the second term, tau I and Ti, what's the minimum of these two? It is always Ti. Is that correct? Is that fine with everyone? We have made these three steps are really crucial. We have converted the integration to summation, and in summation, we are using the property of the Wiener process about the expectation. And then we're just doing algebra as we are going forward. Okay, now let us use what is tau I. Tau I is this alpha Ti, okay, and 1 minus alpha of Ti plus 1. Let me just substitute that here. Summation again. This is alpha ti plus of 1 minus alpha ti plus 1 minus ti. Is that correct? Yeah. Yeah, that's correct. Let me do some simplification here. We have 1 minus alpha into ti plus 1, and we have again, 1 and alpha. Okay. So I think what we will get is something like this. We get 1 minus alpha of summation of ti plus 1 minus of 1 minus alpha of let me just I think we can now let's now put some values of alpha. I think I will make it a bit easy to immediately see what's happening. Let's take two extremes. Let's say that tau I actually is this. Okay, tau I is this, which means alpha will be equal to 1. Consider the limit when alpha is equal to 1. What happens if alpha is equal to 1? The mean of IW will be, this becomes summation tau I, this becomes 0. Basically summation alpha tau I minus summation. Sorry. Basically becomes this. Which basically means if alpha is equal to 1, which corresponds to lower limit of the integration window, this implies that the mean of the integration is actually 0. On the other hand, if alpha was equal to 0, which corresponds to upper limit of the integration window, the way we assign the intermediate value, then what do we get in that case? If alpha is 0, this term becomes 0. What you have is tau I minus 1 minus ti plus 1 minus ti. If you do the algebra, this is basically the increment, right? Tau I plus 1 minus ti plus 1 minus basically increment, and that increment is now added many times. What you will find is this is equal to t. Is this clear to everyone? If you thought clear, please go and repeat the calculation. What this tells you something really interesting. Unlike the deterministic Riemann integrals, the integration value depends on the intermediate point, intermediate value or point at which we evaluate the function. Okay. So it could actually range all the way from 0 to t, depending on the value of alpha. That's just absolutely crazy, right? So you have an integral, and depending on how you integrate, you can get any value between 0 and t. And I have just given you one example with one stochastic function. What that means is that if I now take any general stochastic function of this type, let's call g of some x, times this, where x is a stochastic variable, right? And then you integrate this from 0 to t. This depends on the value of alpha. Where exactly I choose that integration window. Okay. And that makes stochastic calculus a lot more tricky. Okay. And so basically people have settled on two types of calculus. Alpha is equal to 1, that is called Intercalculus, and alpha is equal to, I don't know, it's 0 half. I think it takes the intermediate value. I think it's half. Okay. That's called Stochastic. So, which is why whenever we define an equation of this type, or which is an equivalent way of writing the same will be this, right? You must, which is the case of multiplicative noise. You must immediately say that it follows which calculus, and for all purposes within ecology and many other disciplines, people use Intercalculus. There are some areas of physics people use Stochastic calculus. And in fact, if you don't define what is the calculus you're using, this is not a well-defined mathematical entity anymore, because it can take so many different values. Okay, so that's the one little calculation I wanted to do, a very counterintuitive one. It's like saying, going back to this one, this integral, where was that? Sorry. Now, this integral was always x0 squared by 2, right? Now, what we are saying is that in the stochastic world, this value is all the way between 0 and x0 squared by 2. And that really makes, which basically means that there is no unique calculus in the stochastic world. There are actually many calculus depending on the value of alpha. And the two calculus that people consider are Ito and Stochastic calculus. Okay. So that's where I want to stop today, and we will resume again on Friday. Any questions?
So, what is the standard for for ecological text?
You use Intercalculus. Yeah. We use Intercalculus. And there is a very simple reason for that. One intuitive reason is as follows. Let us look at the second equation, which is increment in x, is given by deterministic terms density. Okay, now if I were to write this now more carefully, this increment delta, del dx is, how do we evaluate this? We take a value of x at time t and multiply by dt. Let me write this in a more discrete form. Okay, and that will give us a deterministic increment. And then we have the stochastic increment. We calculate this multiplicative noise function at xt, and then we multiply it with the stochastic variable. Okay, now this is called the Intercalculus. What this means is that, by the way, what is this? This is basically x of t plus delta t minus x of t, meaning the increment depends on the current state. Increment of the stochastic variable x, population, or the state of the system, depends on the current state and the stochastic jump that happened at this current state. If it was Stochastic calculus, we would write this in a different way. If it was Stochastic calculus, the first term does not change. That would still remain same. The second term becomes really bizarre. Second term actually becomes this. What this means is the increment now depends on the value of the system in a future time. Now, this is something I don't even know how to explain. Okay, so therefore we don't use this. Okay, so this is the Stochastic, and we don't use this. This is used in some physical systems. I don't fully understand why, to be very honest. Mathematically, there is a reason, because Stochastic calculus follows the rules of regular calculus. Okay, whereas Ito calculus doesn't follow the rules of regular calculus. Okay, that's one reason why some people prefer Stochastic calculus. But I don't know why you would ever use it in the real world, because in real world, the increment now shouldn't depend on a future value, right? That's just really bizarre. Okay, so but that's what it means if you choose that.
Sir, there is some similarity between this notation and improved Euler method, right? For numerical integration.
I don't know what is that method you're referring to. I should maybe refer, but I think that's a different thing. No? But that's really more of a differentiation technique. How do you discretize the functions or the derivatives? I don't think it's same as this. That's really more like writing second derivative as x of t plus delta t minus x of t minus delta t divided by delta t, right? Something like that. Right? I don't think it's really same as this.
Okay, sir.
First derivative as t plus delta t minus delta t divided by 2, right? 2 delta t. I think that's a bit different. It's not same as this. Okay. But anyway, I mean, the main point, the take home for you, is because, and I think most of you are here not mathematicians who will deal with the mathematical nuances, but nevertheless, whenever you ever use a stochastic differentiation with the multiplicative noise, you must always state the calculus one equation, and we use Intercalculus, and the reason is what I just described. Okay. And if you want to understand the Intercalculus better, I can also give you a reference right away. It sort of covers more. I would recommend reading chapter number 4 of the book by Gardiner. I think the Gardiner book I have already referred, right? Okay. So it's in chapter 4. And including this example I just told you is covered there. The integral of Wheeler process is also covered there, where you can go back and refer in more rigorously. Okay. Okay, cool. So that's where I will stop now. Okay, so we'll meet on Friday again. Okay. So any topics that you would like? So is demographic noise is one topic I would like to cover, and how that leads to important dynamics. That's one topic I want. How do you even construct demographic noise from first principles? What's the equivalent of mean field approximation for the demographic noise? That's one point I want to cover, and then we will discuss one empirical application, and then finally one sort of broader framework. Okay, that's where we are. We have about 2.5 weeks after this. Okay, cool people. See you then. If there are no questions, see you. Bye.